The convolutional neural network with TensorFlow is what we are going to be doing in this tutorial. So to start, we are going to grab that multi-layer perceptron code, that basic deep neural network code that we worked on in the beginning. You can go to pythonprogramming.net, search for how the network will run. It'll be your first result. Scrolling down to the bottom, we're just going to take that code and we're going to copy it, move this aside, go into TF-tuts. Oops, I opened it twice. Let me close one. And I'm going to new document, and we'll call it cnnexample.py. I actually don't want it in this gedit. Open in Sublime, paste, and here's our code. So we're going to make the changes that we need to make. You should already be able to guess maybe some different variables or changes up here, and then mostly just change this model function, and we should be good to go. So if that was you, you're right. So what we're going to start off by doing is getting rid of these variables. We're not actually using them anymore. Number of classes is still 10. That hasn't changed. We're going to change this to 128 for the same reasons that we did it in the recurrent neural network tutorial. And then now we're going to mess with this neural network model function. And I'm going to just go ahead and delete everything except for 2 of the dictionaries because we're going to use dictionaries. Also, just to note, I am going to try to use the same-ish variable names as you could find in the DeepMNIST for Experts tutorial. It's not the exact same code. They're just scripting this code basically. There is no function as far as I know. And they're actually running the iterations a little different, but so our code is actually a little different, but it might actually even be helpful to you to go through our code and then go through their code and kind of see what the differences are, because you can do TensorFlow in a bunch of different ways. Obviously, it's just like any other thing you could program. So that'll be useful, but also if you're confused about some of the parameters, I suppose, that we set, you could come here and learn a little bit more and kind of keep diving into their documentation if you want, but hopefully I'll explain them as best as possible. Also, as always, if you do have questions, comments, concerns, whatever, you can always leave them below. Moving along, let's go ahead and first we'll call this convolutional neural network. And again, it is going to take data, but we'll replace that with X. Again, same reason we were doing it before. It's just easier, I think, if we just keep everything as X. Now, we are going to, instead of having like layered dictionaries, we're just going to have basically a weights dictionary and a biases dictionary. I think this is a better way to go about doing it. And we'll start with the weights part, and this will be w_conv1. So this is following, actually I said lowercase c if we're going to do it just right. This is following the same kind of names for variables as this tutorial. So if you did weight_conv1, you'll find that, oh yes, look at that. So you probably should be able to see what's about to come. It's going to be something like this. But anyway, you get the following code here. So now what we're going to go ahead and do is do this, only we're not going to define them as straight up variables. These are going in our dictionary. And again, there's going to be not a lot, but some subtle differences here, but it'll be probably a good idea to go through both. Again, if you're confused about how to build your own neural network models, it's good to see as many examples of people doing it as possible. So anyways, moving along, we've got the weights for the first convolutional layer, basically the first convolution. That's, as usual, going to be a TF variable. It's like a TF random normal. It is not anymore going to be 784 by the number of nodes in HL1. We'll delete that. And instead it'll be 5, 5, 1, 32, because those are magical black box parameters right now. Now, this will be 5 by 5 convolution. It's going to take one input, and it's going to produce 32 features, or 32 outputs. Now, I am going to just, oops, really? I can't get away with that, huh? We'll delete that, and I'm just going to copy, come down here, paste, oh my goodness, really? All right, and let's see if I can get away with this. Yes, great. Okay, so we're going to have 4 things in here, obviously not the same things. So you've got your convolution 1, convolution 2, Then you're going to have your fully connected layer, and then you're going to have your output. So we'll just call this out. So the fully connected, I think the tutorial refers to that as the densely connected layer. I think fully connected is the proper term. Densely just means it's not sparse, it's dense. But does dense necessarily mean all of them are connected? I don't think so. So fully connected, I think, is the proper term. Next, you have a 5x5, again, convolution. Instead of one input, it's going to be 32 inputs, and the output, we're going to say, is 64. You can tinker with these if you'd like, but that's what we're going to go with. The fully connected layer is fully connected. It's not a convolution anymore. So we're going to say the image at this point, we're going to say, is a 7x7 image. Remember, we started with 28x28 images. When you do convolution, you're going to significantly compress those images down to be feature maps. It's not even an image anymore. And if you saw a picture of what ends up happening, I wonder if I can pull one up really quick. I'll see if I can. Should have had it prepared. I don't see any in a quick Google search. But they're just like, here we go. This is close. They look like this. Let me pull this over. They look like this. Oh, are you really going to do me like that? Okay, view image. All right, so they look just like this, right? They're just colored squares. And then you might actually look for horizontal lines or edges or whatever and so on. And as you go deeper and deeper, you might look for more complex types of features like eyes here or an entire face and so on. But at their most basic level, they're just these little things. And in this case, this is a 4x4. Okay, but they look like that. They're nothing special. So, so this will be a 7x7, and then by 64, which is from this 64 here, and then we'll have 1024 nodes in the layer. So if you recall, our before our fully connected layers were what? 784, right? That was the input was 784 initially, but now it's a 7x7 times 64 features, and then we're going to just say, okay, we want 1024 nodes there. Then the output is going to be 1024, and then number of classes. So it can be any, 0 through 9. Now we get to the biases, and really the biases are, I think I'm just going to let's do this. I think I'm just going to copy this, paste, so I don't have to like reformat it. Biases. And then we're going to say, rather than weight conv1, it'll be b conv1, b conv, b fully connected, and out can stay the same. That's no problem. Now, for here, the biases would just be 32. Here, 64. Here, what do you think? 1024? Huh. And then here, again, number of classes. So the biases are just for the number of, the output. And then, now that we've done the weights and the biases dictionary, most of the work has already been done. We're going to first reshape x equals tf dot reshape. We're going to reshape x from the input, and we're going to say the new shape is going to be a nice flat 28 by 28 by 1. Okay? Someone in the last tutorial was asking about the reshape, and we covered what did we do? Transpose. There was reshape, transpose, and something else. I forget what the other thing was. But you can always just go to NumPy and take the example, like in the video we use that nice example, and do it in NumPy and just print out at each step of the way to kind of get an idea, because these are kind of like abstract manipulations. This one's fairly simple. This one we are simply reshaping a 784 pixeled image to a flat 28 by 28 image. So that one's pretty simple. I don't think in this one we're going to be doing anything besides reshaping. But in the other one we did like transpose. And transpose is always I can't explain transpose very well, but if you just write out the code and see it happen, there's also like pretty images where they show like transposing happening, but that's not actually how it works every time, so I don't really like that. But Anyway, moving along. If you are confused, I always think the best thing to do is run these out. You could do it in the interactive TensorFlow session as well. I think it's quicker and easier just to open up a quick terminal, use NumPy, and do that. Sometimes the syntax is slightly different in the actual function that you're going to run, but for the most part, it's the same. Like here, rather than, I think in Reshape for NumPy, I don't know that they use brackets. They might use like parentheses or something like that. But anyway, moving along, Reshape's fairly simple. Next, conv1 for that first convolution layer. That's going to be a function we have not yet written. We are going to use the exact same function from TensorFlow. I think it's kind of silly to be to be making a function out of this. It's literally a return one line of code. But they're making a function out of it, and in theory, you could make a more complex function in time. I just don't know that it's absolutely necessary, but we'll go ahead and do what they did in the tutorial. So we're going to say define conv 2D, and we're going to pass the data and the weights here. And all this function is going to do is it's going to return tf.nn.conv2d. And this is basically just going to do that two-dimensional convolution. So take note, this isn't not that, I mean, if this is your first intro to convolutional neural networks, it doesn't really matter. But this is 2 dimensions. You're not going to get the depth in here. So keep that in mind. X, capital W, strides. Let me write these out, and then we'll explain them. But strides, 1, 1, 1, 1, 1. There we go. You're close. And then padding equals same. And then let's write the other function, and don't worry, I'll explain what strides are because we're about to see them again, and then also the k size. Now, define max pool 2D. Again, we're going to pass just x here, and then we're going to return tf.nn.max_pool. Again, from x, k strides is going to be 1, 2, 2, 1, and then strides 1, this will be 2, 2, 1 again, and then padding again will be the same. So, convolution. Recall that when we did convolution, man, my nose is so itchy. When we did convolution, we took that image and then we kind of like slid over a moving window over the pixels, and we just didn't want to skip any pixels, right, at each time. And then with pooling, we were doing basically the same thing, only with convolution, you're trying to extract features. With pooling, you're just trying to simplify things. So in this case, like with strides 1, 1, 1, 1, this is just simply taking, it's going to take your size, and each time it moves, it's just going to move, it's just going to take basically 1 pixel at a time, right, to go through in that convolution. Now, in the pooling, we're going to take a 2x2 pooling here, and we're going to move it 2x2 at a time. And so in this case, that's just moving your pool window twice over. So you're not actually, if I'm understanding that correctly, you're not actually overlapping anything there. For padding, on a 28x28 using such small strides, I don't see why we would ever actually need padding, hopefully. But that would be the case like if you've got a 5x5 window and you've got let's say a 28x28 image, there's going to come a time when you reach like the edge of the image, and to get those last pixels, you might have to have part of your window hanging off, in theory, the image. So how do you want to pad those edges? In this case, we're just saying the same, so it's just going to pad those same exact pixels to the edge. So those are your 2 functions. Again, it's not absolutely necessary to make them a function, but it's conceivable you could have your convolution be doing a lot more complex things, and then it's not just 1 line of code. So we'll leave it that way, I suppose. So, oh, did I call it case size? Okay, this is the size of the window. Size of window. That was going to give us an error. And then this is the actual movement, let's say, of the window. Okay, so this is the size. It's a 2x2. We're moving that window 2 pixels each time. So there is no overlap here. As opposed to here, where your stride is simply 1 pixel over at a time. Now, those are the last functions we need, so we're coming back down underneath that reshape. And what we're going to do now is we're going to say conv1 is going to be conv2d, which we just wrote. We pass x, and then the weights will be, actually we can just pass weights like this. Weights, I'm pretty sure the parameter is weights equals, but we're going to do this because it's the second parameter. W underscore conv1. So that's our conv1. Then we do pooling. So we're going to say conv1 equals max pool 2D. Again, we just pass the data, but the data this time is not going to be x. We're actually working with conv1. Remember that that full layer is actually the result of the convolution and the pooling, and together they are a layer. So actually we're going to apply this pool to that convolution. And then we're going to take conv2, and that's going to be, in fact, let's just take this, copy, paste, and this will be conv2. This, the input to that secondary layer, that's not going to be x anymore. That'll be conv1. The weights, conv2. Max pool will be against conv2. Now, we're going to do the fully connected layer. So FC, that's going to be tf.reshape. We're going to reshape that conv2, and the shape will be that a -1, and then 7 by 7 by 64. That's what we did up here. So we're reshaping that. Next, what we're going to say is fully connected equals tf.nn. This should start looking relatively familiar. Rectified linear of the tf dot, and what are we pretty much always going to do? A matrix multiplication of what's the input, FC. What are going to be the weights? It's going to be weights. And this will be for the fully connected layer. Matmul. And then plus. Remember that time I put the plus in? We did the TF add. Ugh, horrible. Biases. And then for the BFC. Oh, my nose is just dying. Okay, now we're going to do finally the output layer. Not have so much space. So output will be, again, because keep in mind, remember, the fully connected layers are super simple. They basically just do this every time, as opposed to the convolution layers. Now, the output, again, is just going to be tf.matmul, and this time the input is FC, that fully connected layer. The weights will be the weights for the out layer, matmul, and then we're going to just do plus the biases for the out layer. And that's it. So then we take convolutional neural network, copy, paste, and we should be finished. Let's see what happens. Will this be the first neural network that we've built that doesn't have an error on running? If I was putting money on it, I would say no. Python 3. Really? Oh, we use CNN, I think. Could it be? Oh my goodness. Let's see if we actually train. Guys, can you believe this? Oh my gosh. I hope this recording is working. I'm looking at like the output and it's not looking so hot. Anyway. We'll see. We will see. So we are running through, I think we did probably 10 epochs, and we didn't move that variable, which hopefully we would have moved, but that's okay. Oh, it's going so slow. I think it's because I'm recording and it just really messes with my recording. Okay, accuracy 97.5%. Actually, I believe that's worse than the recurrent net that we did. But it's because the size of the data is not ideal. So the recurrent net actually can seemingly get by with smaller data sets, at least from what I've found. The ConvNet will be superior with a much larger data set. The other thing that I do want to just show is, especially with the ConvNet, dropout. This idea of dropout is pretty important. The idea of dropout is like, from our brain, for example, not every neuron actually works in our brain. So neurons sometimes are dead neurons. Okay, so with dropout, we're kind of like mimicking just a missing neuron from time to time. So you can add dropout to your neural networks. It seems to be the most popular with the ConvNet, so I'll go ahead and show it here. I can't remember if it's in this tutorial. Let's look for Yep, it is. Okay, so again, even with dropout, you can look at the example here. We're going to add ours just to the end anyways, but yeah. So after our x and y variable definitions, let's go ahead and add a keep rate. The keep rate will do 0.8, and then keep underscore prob will say is tf.placeholder, and it's going to be tf.float32. Okay, now what I'm going to change is down here. Someone made fun of me for using notes in my tutorials. Just for the record, this is the first time I'm teaching at ConvNet, so you should be thankful I'm using notes. Now, let's go down to, it should be just at the end of this fully connected layer is yeah, we'll just add it there. I think that's all we're going to do is just add it right before the output. So you could, in theory, apply dropout like right here. You could say fully connected equals tf.nn.dropout. What are we going to apply that to? That fully connected layer. What's the rate of keeping is keep rate? Let's look that up really quick, actually. Now that I am looking at that, that doesn't sound right that it would be .dropout and then it would be keep rate, but let's find out. tf.nn.dropout. TensorFlow docs, link me to the right thing. Dropout. That is keep prob. Okay, cool. And you can even throw in these I had no idea they even had these other parameters. Anyway, all it does is compute a dropout, and we're going to just throw in that keep rate. So basically 80% of our neurons will be kept. Whoops. Sorry. Now, that should be all we have to do. Can we go for 2 models in a row of changes and no errors? I really think that's all the 2 major changes to add dropout would need. So let's run it. See what happens. So let's wait, see if we're actually training, and then I'll talk. Okay. Wow, that's a lot of error. That's like significantly more error than the other one started with. But anyway, dropout is probably gonna add a little bit more error, but the idea is to, I hate to say it's not really so much a form of noise. I don't even know how to describe what dropout's necessarily like. It's kind of its own unique snowflake. But in this small of a data set, dropout's probably not actually going to help us at all. But again, in a much larger data set, dropout is going to help because they're going to, and in fact, we even did worse. Let's run it one more time. Dropout is kind of like not everything is exactly the same, and sometimes like maybe one neuron is given way too much weight or something like that. So these things can happen, so dropout can kind of help fight those kind of local maxima kind of things. But anyway, once we're done with this, we'll be done with this tutorial. But again, in general for image data, even though in this case the recurrent net actually did better, spoiler alert, I'm more of a fan of recurrent nets anyways. But in all reality, on image data, generally the convolutional neural network, it still did worse. Under 97. The convolutional neural network is the champion. You're just going to need a bigger data set. And in this case, I think we're using 50,000 images and 10,000 tests, if I recall right. Something like that. It's not a huge number, and in reality, you would want a very large number to work with. So anyways, that's a convolutional neural network in TensorFlow. If you have questions, comments, concerns, whatever, feel free to leave them below. Otherwise, as always, thanks for watching. Thanks for all the support and subscriptions. And until next time.